Hi everyone, welcome to the top 10 CI/CD security risks talk. My name is Omer and I'm leading research at Cider Security.
And I'm Daniel, CTO and one of the founders at Cider Security. For those of you who don't know Cider, we're an Israeli startup and we've built a platform that allows organizations to build, orchestrate, and manage effective AppSec programs for the modern software engineering environment. And let's dive into the top 10. So before we talk about the top 10 CI/CD security risks, let's dive into what CI/CD security actually means. To understand this, we first need to understand what the engineering ecosystem has evolved to over recent years. In today's reality, the engineering train is moving faster and faster, with releases being conducted on a daily or hourly or sometimes minutely basis, with the stack being comprised of a much more diverse and dynamic set of languages and frameworks, with the fact that it's much easier and takes a much shorter time to adopt a new technology or framework, with not only applications being codified, but our infrastructure and our data centers being managed inside our source control, and then with a lot of manual processes that are replaced in favor of various automations that make up for our continuous integration and continuous delivery processes. And when we look at the building blocks that comprise the engineering ecosystem, we have different types of systems and then different types of objects, artifacts, processes that are being moved all the way from the engineer's workstation to production, with a fusion of human collaborators and applications and services accessing these systems, and of course, a wide variety of third parties, as well as access tokens and programmatic credentials that are spread throughout this environment. And the challenge for us as defenders is that the reality doesn't really look like what we're seeing right now, but rather more along the lines of this. Even in a small startup, definitely in a big organization, the engineering ecosystem is a big, chaotic, high entropy environment that's constantly growing and changing and evolving, with every one of these building blocks being potentially connected to one or more of the others. And then the complexity for us as defenders that are tasked with coping with this challenge stems from how deeply familiar we need to become with the inner workings of this environment in order to properly understand what are the different risks and what security measures are required. We need to understand what systems comprise our engineering ecosystem, what repos we have in source control, what languages and frameworks are being used, what pipelines run in our CI and CD systems, how do CI pipelines connect back to source control to fetch code, build it, and test it? What are the programmatic tokens and credentials that exist in our CI and CD solutions? And what is the different permission and scope for each and every one of them? And then how do CI and CD pipelines ultimately take code, build, test it, package it, upload artifacts to artifact repositories, container images to container registries, and then which pipelines and using which method and what permissions are ultimately responsible for deploying workloads to production. But that's not where it ends. Once we know all this, we need to understand which humans and which applications and services have access to which parts of this ecosystem and how. And ultimately, what we're seeing right now is what our attack surface really looks like. This is how an attacker looks at our environment to analyze the different paths through which it can be abused and the different vectors that can be carried out. And then in order for us as defenders to be able to effectively derive the risks within our CI/CD ecosystem, what we're seeing right now, this is the level of familiarity and understanding that we need to have with how our engineering ecosystem looks like under the hood. And so the evolution that we mentioned of the engineering ecosystem resulted in a massive change in what the organization's attack surface looks like and what the CI/CD risk surface looks like. And it created a wide variety of new attack paths and vectors. And CI/CD security is really about that effort that we as defenders need to take to adapt to these changes. And the reason why we're talking about CI/CD security now is because of how recent years, and specifically 2021, were pivotal in relation to CI/CD security, in the sense that attackers were focused on hacking CI, running malicious code in CI, leveraging CI, CD systems and environments to get to production. It began with SolarWinds and went through the CodeCov breach and PHP and Dependency Confusion and a lot of other incidents which ended up incentivizing us to roll up our sleeves and to carry out the top 10 CI/CD security risks initiative.
So Daniel and I have been working for several years with many organizations on improving their security posture, and we often encountered organizations that had high impact flaws and possible attack vectors in their engineering ecosystem, which is one of the main challenges that Cider's technology aims to solve. But the gaps we saw were not just around the lack of technologies. Another thing that we found that was common to all of these organizations is the lack of knowledge and methodologies of how to protect their CI/CD ecosystem. And even more importantly, to understand what risks they should protect against. So from day one at Cider Security, we knew that optimizing the state of CI/CD security wouldn't only require a strong technology. We wanted to contribute to the InfoSec and dev communities by sharing knowledge and methodologies to assist defenders succeed with this challenging this evolving attack surface around engineering environments. And this huge gap of knowledge for defenders in the areas of CI/CD led us to creating the top 10 CI/CD security risks initiative. It's a comprehensive project that we worked on for 9 months, detailing the top 10 security risks in CI/CD environments. The initiative is the results of 3 main sources. So first is the extensive research and analysis based on our experience working with lots of organizations. Second is discussions that we've made with some of the industry's top experts, and we'll see their name in a moment. And third is publications of incident and attack techniques within the CI/CD security domain, which we'll demonstrate later on as part of this talk. Now, all of the top 10 risks are well detailed in the document that you can now see on the screen. Each of them is built of a definition, a technical description, the impact on the environment, suggested recommendations, and references to notable incidents that were made possible due to the existence of these risks. You can find the entire document on our website at cidersecurity.io, and you can also reach out to the Cider Security Research GitHub organization, where you can suggest your own additions to the documents. So now, after all of these teasers, here are the top 10 CI/CD security risks. You can see them now in the slide, along with their IDs from insufficient flow control mechanisms to insufficient logging and visibility, sorted by the combination of their impact and probability. Now, as I just mentioned, it was important for us to collaborate with security professionals on this project and to gather feedback from bigger and smaller companies and from different roles, both technical engineers and CISOs. When we reached out to the experts that you can now see on the screen, they were all very excited to take part in this project and provided invaluable feedback and additions. So I'd like to take this opportunity and thank all of the talented experts in this list for their contribution. So after an endless number of breaches that we've analyzed and environments we've seen and many discussions that we've made, we thought, what is the best way to explain the top 10 risks in the time that we have left for this talk? And the best idea that we came up with was to open the 40-page PDF and simply read it to you. So let's start. No, I'm kidding. We don't have time for that. What we really decided to do is to deep dive into 5 case studies covering some of the most notable hacks and attack techniques in the CI/CD domain from recent years, which we analyzed as part of our research for creating this document. And in each case study, we'll break down the anatomy of the incident and distill the risks out of the top 10 list that made it possible to occur. So let's start.
All right, so our first case study is the PHP Git infrastructure compromise. In March 2021, an attacker was able to gain access to the self-hosted Git infrastructure that was used by PHP. The attacker created a new version of PHP containing a backdoor and then pushed the code to the Git server while signing off on the commits as if they came from legitimate PHP maintainers. At the time, PHP did not require any additional approval process or review prior to merging new versions, which is what enabled the attackers to leverage the access that they had to update the production version of PHP being pulled by consumers. And so for a short time window, there was a malicious version of PHP being distributed to consumers that allowed remote command execution on any website running the hijacked version of PHP. So let's discuss the different risks out of the top 10 that were exploited in this scenario. The first one is risk number 1 in the top 10, and it is insufficient flow control mechanisms. It refers to an attacker's ability to abuse CI/CD misconfigurations to single-handedly push malicious code or artifacts down the pipeline without a requirement for additional approval or view. In our case, as we mentioned, PHP did not have any process for preventing direct, unreviewed changes of the PHP source code, which is how the production version of PHP was modified. Risk number 7 in the top 10 is insecure system configuration, and it refers to flaws in the security setting, configuration, and hardening of the different systems across the pipeline. These flaws typically create low-hanging fruits, which are then used by attackers to penetrate and move laterally within the CI/CD environment. In PHP's case, it was managed using a self-hosted Git infrastructure that had insufficient security hardening and was compromised and breached during the incident. Now, naturally, PHP discontinued the usage of the self-hosted infrastructure immediately after the incident in favor of a SaaS GitHub, which they are still using today. Risk number 9 is improper artifact integrity validation. It refers to a lack of mechanisms for validating the integrity of code and artifacts that allows an attacker with access to one of the systems in CI/CD to push malicious code or artifacts down the pipeline. In PHP's case, the signed commit mechanism, which verifies the author of each commit using a cryptographic signature, was not in use, which is what allowed the attackers to masquerade as legitimate PHP maintainers, despite not having the private key of the actual maintainers. And then the last risk, which is relevant here, is insufficient logging and visibility, risk number 10 in the top 10, and it allows malicious activities to be carried out within the CI/CD environment without the defenders having any correlating detective or investigative capabilities. Now, logging and visibility is obviously an important building block for any environment that's targeted by adversaries, of course, CI/CD included, but what Omer and I saw again and again with the organizations that we work with, even sometimes in the most mature organizations with the most mature security programs, is that the majority of times, organizations don't have the proper monitoring and logging and visibility and security oversight over those systems and processes and environments within the CI/CD. This was also true in relation to PHP, which detected the breach only after the malicious commits had been made, and is of course relevant to some of the other incidents that we'll discuss in the upcoming slides. So of course, wherever relevant, we will mention specifics, but generally speaking, logging and visibility is an essential base layer for coping with any type of CI/CD security incident.
Okay, moving on, let's talk about the Stack Overflow breach. So one day in May 2019, the Stack Overflow team was alerted by members of its Stack Exchange community that a user that nobody knew before was suddenly granted with high privileges over the system. Now the team started investigating how it happened and discovered a much deeper incident that even led to leakage of their source code. Now it all began with anonymous attackers from the internet who successfully gained access to what the company names the dev tier, which is an internal environment which is mainly used for testing. The attackers tried using various functionalities through this dev tier and eventually put their hands on a service account password that was stored in clear text in one of the configuration files. Now, this account was used in the past for programmatic access to access TeamCity, which was the CI solution used by Stack Overflow. But even though it wasn't in use anymore, the credentials were still valid. And not only that, the attackers could access TeamCity from the internet and to log in with this account, even though it was never used for interactive login before. Now, when the attackers logged into TeamCity, there was a security misconfiguration around role management that granted admin privileges on their account by default on the TeamCity instance. Okay, moving on. The attackers really wanted to access the source code of Stack Overflow, so they tried to log into their GitHub organization, which was a self-managed GitHub enterprise instance, which was also accessible from the internet. Now, this attempt failed because this organization was enforced all users to have 2FA. Now, using the TeamCity admin privileges, the attackers stole a GitHub SSH key from the system. And since SSH keys are not restricted with 2FA in GitHub, the attackers were able to use it to access GitHub and to access the repository stored on GitHub and to leak their source code, which also contained plain text secrets to other systems. That was the Stack Overflow breach. These are the risks that made it possible to occur. Let's understand what they are. So the first one is risk number 2 on the list, which is inadequate identity and access management, which refers to poorly managed identities, both human and programmatic, across the different systems in the engineering ecosystem. Now, in the case of Stack Overflow, there were various issues around identity and access management. First, the service account that was no longer in use for a while was never revoked. Second is, again, around the service account that was used for programmatic access, but the attackers were able to log in interactively to the system using this account. And also these admin privileges that were given to any user accessing the system by default. Now, it's also important to mention that even though 2FA was enforced in the Stack Overflow GitHub organization, which prevented the attackers from accessing the code base in the beginning of the attack, it wasn't enough to stop the attack from happening. Another risk that led to this breach being so successful was insufficient credential hygiene, which is obtaining and abusing secrets and tokens spread throughout the CI/CD ecosystem due to poor access controls, insecure secret management, and overly permissive credentials. Now, this risk is often thought of only in terms of secrets in the source code, but secrets are spread across all of the CI/CD systems, like the CI, the CD, container images, and hygiene should be maintained in all of these systems. Now, in the case of the Stack Overflow breach, credentials were stored in clear text in repository commits, in configuration files, and in the build system. Now, once the attackers got access to each of these systems, they could easily leverage this access to move laterally to other systems. And an additional risk, which is relevant and Daniel just mentioned, is insecure system configuration. The self-hosted GitHub and TeamSeed instances were accessible from the internet, even though it wasn't required.
All right, next up is environment variable exfiltration through CodeCov. So CodeCov is a tool that allows engineers to collect metrics about code coverage, and one of the ways of using CodeCov was for configuring the CI to fetch a CodeCov script hosted in CodeCov managed infrastructure and then executed directly from within the build environment. In January 2021, CodeCov published that attackers were able to obtain access to that GCS bucket hosting the script and modify the script in a way that caused it to exfiltrate the CI environment variables. As a result, any pipeline that was configured to fetch and directly execute the CodeCov code without validating its integrity was infected, with a malicious code sending the CI environment variables to the attacker's server. In CodeCov's case, we're not going to analyze the scenario from the perspective of CodeCov, but rather from the perspective of the thousands of organizations that were impacted by the fact that CodeCov was breached. So let's begin. The first risk is risk number 5 in the top 10, and it is insufficient pipeline-based access controls. It refers to an attacker's ability to abuse permissions and access granted to pipeline execution nodes and environments for moving laterally within or outside the CI/CD ecosystem. And many organizations dealing with a CodeCov breach were severely impacted because their CI environment was configured in a way that exposed CodeCov to many more environment variables, secrets, than they actually needed. Now, all of these environment variables and the secrets stored within them were sent to the attacker server. This obviously included production credentials that the CI environment actually used for deployment. And this fact obviously made response and recovery far more complex. And the takeaway for defenders here is the importance of adopting the assume breach mentality around usage and implementation of third parties in CI to make sure that even if a third party is compromised, the extent of resources and assets that the code of the third party can access is minimal. Risk number 8 is ungoverned usage of third-party services. Now, our CI/CD attack surface consists of an organization's organic assets like the source controller CI, and then all the third-party services which have some sort of a level of access or permission to those third parties, to those organic assets. and risks around ungoverned usage of third parties exploit the extreme ease with which third parties are typically granted access and permissions to resources in CI/CD, a fact that usually creates a significant expansion of the organization's attack surface. In CodeCov's case, what the majority of security organizations were trying to figure out was, one, whether or not CodeCov is in use by the organization, two, where CodeCov is in use, and then three, what type of permissions and access does CodeCov have within the environment. And one of the main takeaways for defenders from this incident is the importance of having that same level of understanding and visibility available at all times for any type of third party that exists in the environment, to make sure that stale or overly permissive or insecure third-party services are identified and dealt with, and to make sure that the organization has the proper investigative capabilities in case of an incident. As for the risk we already discussed, insufficient credential hygiene risks were exploited in every environment where the secrets accessible to CodeCov were overly permissive, providing the attackers in many cases with administrative privileges over production environments. Improper artifact integrity validation, which was exploited in any organization that did not validate the integrity of the CodeCov script prior to executing it, a measure which would have detected the script had been tampered with and prevented its execution. And of course, insufficient logging and visibility, relevant to all organizations trying to understand exactly when and where they were impacted as a result of the fact that CodeCov was breached.
Okay, case study number 4, the Travis CI secret exposure. So for about a week in September 21, there was a security flaw in Travis CI that exposed the secrets stored in all public repositories which are linked with Travis, so attackers could easily access them. Now, any SaaS CI solution by default prevents pull requests that originate from forks from accessing CI secrets. The CI secrets that Daniel just mentioned usually have high permissions to production systems, and only repository members can access these secrets, which is disallowed for other users that originate from the internet. Now, that's also how it works in Travis. Secrets are encrypted by engineers using a public key, while the private key is only accessible to Travis. When everything works as expected, Travis doesn't decrypt secrets when running on pull requests that originate from forks. This prevents anonymous attackers from the internet from exposing these secrets. Now, back in September, the security mechanism didn't work in Travis for a whole week. Let's see what happened. So attackers could fork a public repository that contains encrypted secrets meant to be used in Travis CI, and then they could issue a pull request from this fork and add malicious code in the Travis configuration file, which is stored in the repository, that exfiltrates these secrets out of the pipeline job. Now, as we just said, normally Travis shouldn't have decrypted these secrets, but this flaw made it do so and allowed anonymous users to access these secrets in any public repository. These are the risks that could lead an organization to be vulnerable to this security flaw in Travis CI. The first one is risk number 4, poison pipeline execution, or PPE in short, which refers to the ability of an attacker that has obtained access to an SCM repository to run malicious code in the CI, despite not having access to the CI, by manipulating the pipeline configuration. This can be done by modifying the CI configuration file directly, or other files in the repository which are executed as part of the pipeline. Now, in the case of Travis, PPE is the method of how attackers could take advantage of the security flaw, modifying the configuration files of Travis pipelines so when the pipeline runs, the secrets would be decrypted and exfiltrated out of the pipeline. All that simply by forking the public repository and creating a pull request out of it. An additional risk that we already covered is insufficient credential hygiene. If secrets that shouldn't be used in the pipeline were accessible, or stored credentials that were granted with excessive permissions, it would increase the impact of the attack, and also of insufficient logging and visibility, because when this flaw was discovered, many organizations had difficulties to quickly identify if they have any public repositories which are linked with Travis pipelines and that contain encrypted secrets. And then they wanted to quickly check if there are any pull requests that were created in the time where this flaw existed, to identify an actual breach.
Our last case study is dependency confusion. So dependency confusion became famous after a publication by Alex Birsan in February of 2021. Let's break down how the attack works. Our engineering organizations have both developer workstations and build environments fetching dependencies from both public repos as well as internal repos that are typically used for internal packages. In a dependency confusion scenario, the attacker reveals, using one of many potential methods, the name of an internal package of an organization, and then uploads a package with the exact same name, but with a higher version, to the public repository. Poorly configured package fetching processes, which are configured to always fetch the highest version of a package regardless of its source, would end up fetching and installing the attacker's malicious package rather than the harmless internal package they intended to install. This vulnerability affected Apple, Microsoft, and dozens of other companies, but thankfully dependency confusion was published by a white hat and not as a result of a breach, but it is still unknown the extent to which malicious actors were exploiting and abusing dependency confusion prior to this publication. There are three main risks worthy of mentioning in this context. The first one, dependency chain abuse, and it refers to a situation where dependency fetching configurations are abused to cause an unsuspecting client to fetch and execute a malicious package on the host pulling the package. Dependency confusion is one method of abusing the dependency chain alongside dependency hijacking, typo squatting, brand jacking, and the fact that dependencies are so widely used, combined with the fact that dependency fetching processes are highly prone to human error, is what makes dependency chain abuse one of the most impactful CI/CD risks, security risks out there, because it allows malicious code to be executed on critical CI environments without the attacker needing to have any type of access to any one of the organization's assets. Additional risks we already covered are insufficient pipeline-based access controls relevant for all vulnerable organizations which downloaded and executed malicious packages in overly permissive execution environments. And of course, it goes without saying that logging and visibility was critical to any organization trying to assess whether they were whether the environments were abused by dependency confusion. So we covered the 5 case studies. Let's talk about how we apply the top 10 CI/CD security risks in our day-to-day. First, a shift in mindset. We need to understand that the attack surface has changed and that engineering environments are a big part of the organization's attack surface, and even the most sophisticated hackers are targeting CI/CD. This then requires a different approach to AppSec. AppSec is no longer just about securing the code, but rather the need to provide a full-blown security umbrella over the entire software delivery chain, all the way from code to deployment. The AppSec program needs to be built upon a comprehensive mapping of our engineering ecosystem, and we need to be able to build the technical DNA of our environment to have a true understanding of what our attack surface looks like, all the way from code to deployment, consisting of both our organic assets as well as any third party that has connectivity to our organic assets. Once we have that technical DNA, we need to build a continuous analysis against the attacker's perspective, leveraging that DNA to understand what risks our environment is susceptible to, using the top 10 CI/CD security risks as reference. And then once we're able to continuously detect what types of risks our environment are exposed to, we then need to continue to build and optimize our CI/CD security programs to make sure that there aren't any redundant risks introduced into our ecosystem as a result of the way our engineering ecosystem is set up. So thank you very much. We enjoyed talking to you a lot.
If you have any questions, we'll be happy to address those.
Thank you.